What's up, you guys? It's time I walk you through on how I solved the MIT Integration B qualifying exam for 2025. So let's go ahead and get started with the first problem here. So right here, I notice immediately that you can factor out square root of x, and then you notice that square root of x plus 1 would cancel out the denominator. So here with this integral, I would just, this is pretty much the integral of the square root of x dx. This is, you could factor this out, right? And we had like 1 plus square root of x on the denominator, right? So of course that's where this comes from. So this, we know, we've seen this so many times. We know that this is equal 2/3 3/2 plus c. Okay. For the second one, this one's also easy, right? This plus 1 right here is a distraction. So move that forward, or move it here at the back of the integral, behind the integral. Pretty much, yeah, just move this constant in the front. Try it, right? And then you immediately see that this is just a basic u substitution. So here you should already know this is e times ln of e to the x plus 1, right? That's the feel you should already get. You know, this constant, move it to the front. Move any constants that's like distracting you, just move it to the front, and then realize, oh, it's a basic u substitution. So this is easily equal to e times ln of e to the x plus 1. Okay. Here, this one, honestly, I don't remember my trig identity for sine 3x, but here's how I notice. I'm like, okay, there's a cube root, and we have this, right? So in my head, it's like, what is the purpose of this integral, right? Why is there a cube root here? So in my head, I'm thinking there has to be, you know, this has to equal to sine cube or cosine cube. But I don't remember, right? I know, I only remember the coefficients, like, oh, it can't be like 3 sine cube, otherwise the 3 would have factored out. And I'm pretty sure it's not 3 sine of x minus sine cube, because I remember sine cube has a coefficient, which was 4, because I remember 3 and 4 were the coefficients for it. So that's how I just kind of slowly progressed to memory of what is sine 3x. But if you don't remember sine 3x though, what you can do, this is actually the long way. I don't think there is any short way, but if you don't remember, unfortunately, the way this is derived is by complex analysis. So this is literally equal to this, which is, or I'm sorry, not exactly. This is equal to the imaginary part of e to the 3ix. And by de Moivre's theorem, this is, we'll put imaginary, this is cosine of x plus sine of x cubed. So you have to cube it. So now, what we have here is we have like cosine cube plus 3i cosine cube sine plus 3i square of cosine sine square plus, and then this, right, sine cube, right? Of course, we only focus on imaginary, so we don't care about this. So sine 3x is equal to 3 cosine square sine plus, oh, I'm sorry, not plus, because this is a negative, so minus sine cube, right? I cube is a negative number. And then to put everything in terms of signs, you just let this be 1 minus sine square. So we get 1 minus sine square, s minus sine cube. We get 3s minus 3s cubed Did I do this correctly? Yes, I did. And this is where, right, sine 3x is equal to 3 sine of x minus 4 sine cubed. So this is how you remember it, right? Well, this is how you kind of, if like for emergency purposes, like you don't remember sine 3x, this is how where it comes from. Okay? And as you can see, it's 4 sine cubed. Right. So this was like kind of in my head. I get up to here, and then I had to be careful. And I had to write this portion down. And like, oh, okay, it's like -4 sine cubed. So, yeah. And that's where I got the cube root of 4 and sine of x dx. And then that's where my answer was negative cube root of 4 cosine of x. Here, this is just simplification, right? Use logarithm rules. Here, take this out, right? So let me go ahead. For those who can't do it mentally, I got you. Whoa. Okay, so here we're going to take that log x to the power of x out, and this itself is literally x log of x, right? You take this power out here, take it out, you get x log x. So what we actually have is x ln of x squared, right? Now this cancels out, and this is literally what we have, 1 to e to the e, right? Let u equal ln of x, you get 0 to e, right? And that's where e cubed over 3 comes from, right? Just by power rule. So that's what I got, and that should be correct. Yeah. Here, what do you notice whenever you see something like this? Is there something suspicious about the bounds? Yes, right? This is an odd function, so this is equal to 0. Another one here, right? Super easy. This is 1 cosine secant x, 1 sine cosecant 1. So this whole thing is equal to 1, so what do we get? 2 pi, right? Here, something suspicious here. This one, so here, notice that I have log square, and then some weirdness going on here, right? So, what I do, the first thing that comes to my mind is when I have awkward functions like this, out of nowhere, where they don't, like, a logarithm and a trig, like, come on. Like, this is very awkward, right? And I have a square here at the bottom. Something suspicious is telling me that this is a reverse quotient rule. You can simplify it or kind of like format it in a different way to give yourself like reassurance to make sure that what you think is correct. So like ln of square, right? Then I have x, I'm going to bring this x to there, or kind of divide x technically, dividing x top and bottom. So here I have ln cosine x and I have like minus sine of x over x. What does that look like to you? Reverse product rule, right? And of course, what is g? G is ln of x. F is what? This is f prime of g, right? Because in reverse quotient rule, it's f prime of g minus fg prime. In this case, f prime is cosine, therefore f is sine of x. And so that's where my answer is sine of x over ln of x plus c. And that's the answer. Here, right? So at first, this did throw me off. I was like, why would they put such a bashy integral? And then I realized the purpose. Oh, wait a minute. There's an exponential function and a logarithm function with the same base. Huh. Very suspicious, right? So, what I did is I do a test, right? I do a test. Let y equal 2x minus 1, right? And I just want to quickly find the inverse, just to check. Okay, well, we have log base 2 of y, x minus 1 right? So x is equal to like log base 2 y plus 1. And here I was confused. I'm like, this doesn't really match, right? So maybe I have to do some sort of weird inverse trick. But then I realized, oh, wait a minute. 1 is equal to log base 2 of 2. And so, what is this? That's exactly what we have here. And so they are indeed inverse of each other. So by the sum of inverses, this is equal to 2 squared minus 1, which equals to 3. So the answer to this is 3. For those who don't know, right, AB f of x, if you have the sum of your function and then plus the inverse of f of b, f of a, this is equal to b f of b minus a f of a. Okay? In this case, we had bounds where this is 1 and 2, and this is equal to 1 and 2, such that b is equal to this, and a is equal to f of a. Okay? So that was our special case here. This one stumped me a little bit because I was like, oh no, I'm not motivated to do beta function. But then I realized, wait, what am I doing? This is 1 minus x to the power of 2025, and this is x to the power of 2024. So, literally all you had to do is let u equal 1 minus x to the power of 2025. That's all you had to do. Let u equal 1 minus x to the power of 2025, right? And you should get like u to the power of 2025 over 2025, right? And then solve, and then you just compute your bounds, and your answer should just be 1 over 2025 times 2026. Okay? Very easy, very simple. There is no beta function. You don't need to do that here. Okay. 10 and 11 I skipped, so I'll go through that later on. So I skipped this because this looks nasty. I skipped this because I don't want to work with that yet. And then I came across this. So this one intrigued me and I actually wanted to try it. So what is that? So whenever you see something like that, the easiest thing to look at it is to put it in exponential form, right? Put it in exponential form. Here we have 3 over 1, but remember that these are roots. So roots are like 1 over n, right? If I have an nth root, that means that it is x to the power of 1 over n. So this means that I have 1/3. So I have 1/3. Plus, and then here you have to be very careful, right? When you compute the exponent for this x, it is not 1/2. Oh, I'm sorry, 2/4. You want to leave it as 2/4. You'll see why. In series like this, you want to leave it unsimplified so that you can generalize a pattern. In this case, I have 2/4, but it is not just 2/4, right? It's not just 2/4. It's also, you have to know, this is a common mistake. You have to know that this x is not inside here, but also inside here. So it's 2/4 times 1/3. Okay? So do not forget that. That's a very common mistake. Okay? And then here we have 3/5. Okay, and then don't forget to times 2/4 times 1/3, right? Because it's inside of these roots as well. And then we have 4/6 times 3/5, etc. Right? And do you see a pattern? Well, I do. Right? There is, we can turn this into a sum. Let's let n equal to 1. And I notice that this is n factorial, right? And then I notice that this is also like some sort of n factorial as well, starting with 3, right? So it's always starting with 3 times whatever. So with n equals to 1, I need n plus 2 factorial, right? Because I'm starting with 3. So, but however, be careful. 3 factorial is 6. This is just 3. I need a 2. Right? I need a 2 on everywhere. I'm missing a 2 on the bottom. So what I do is, because this is equal to like 3 times whatever without the 2, times 2, right? I need a 2 on top. Okay? Because if I'm doing factorial here, 3 factorial means I need times 2. So if I need times 2 here, I need to multiply 2 here as well. If I need 2 here, I need to multiply 2 here as well, so that this actually does become a factorial number. Otherwise, I'm missing a 2. So that is why I have a 2 right here. This nearly messed me up. I had to double check. I'm like, wait a minute. This isn't fully a factorial. I'm missing a 2. So that 2, if you missed a 2, that will screw you up. Okay? So be very careful on this one. This was very evil. We go ahead and simplify that sum. N equal to 1, right? We have 2. This is n plus 2 factorial is equal to n plus 2, n plus 1 factorial. So this n factorial and n factorial cancels out. So we are left off with n plus 2, n plus 1. Whenever you see something like this, just do partial fractions. It's a lot easier to look at it because it's more likely to be a telescoping sum. Okay? So n plus 2, n plus 1. Just kind of do a heavy side method. Right, negative 2, negative 1, negative 1, 1. Okay. So what we have is we have 1 over n plus 1 minus 1 over n plus 2. This is indeed a telescoping sum, right? Plug in 1, get 1 minus, I'm sorry, what am I doing? That's not 1, that's not 1. N equals to 1, you get 1/2, right? And 1/3 here, and 1/3 here to 1/4 here, 1/4 here to 1/5 here, etc. blah blah blah, right? Yeah, this cancels out, this cancels out. They telescope, right? And then at the very back to infinity, it's just going to converge to 0, because if you take the limit as n approaches to infinity, it's just going to equal to 0. So what we have here is that this is equal to 1, right? 2 times a half is equal to 1. So our integral, this is x dx. So our answer is x squared over 2 plus c. Even though you don't need the plus c, it's a habit. This one, I already knew immediately. Oh, like, you let u equal x e to the x and see where it goes. If my du is x plus 1, which I see, right? So I could literally, it's not exactly in my head, but just letting u equal to x e to the x, I knew immediately, oh, this is like, it matches. And I notice this, you can factor x times x plus 1. The x goes from, shares one of the x to the e, shares one of the e to the x's. So that's how I knew let u equal x e to the x, and you get u over u4 plus 1, and your answer should be like 1/2 of inverse tangent of x squared times e to the 2x. Okay, so very basic u sub, let u equal x e to the x, and you're good to go. So intimidating, right? But it's a very easy integral. This one I will show you. Clearly, you can factor this, right? So we know this is secant square plus tangent of x, secant square minus tangent square of x. And here I already knew this is equal to 1 by trig identity, right? Tangent square of x plus 1 is equal to secant square, right? So secant square minus tangent square is equal to 1. And that's where this is. So this is 1. And so I was left with this integral here. And here I want to turn this into secant square minus 1, right? So I originally have secant square. I'm sorry, not originally. So this becomes 2 secant square minus 1 dx. So an answer is 2 tangent of x minus x plus a. Okay, very easy integral. Hard to maneuver. It scares a lot of beginners, right? You just factor and then notice that this is a trig identity that equals to 1. Okay, so just want to show that because that's not very easy to see. Here, this one, I see this so many times. I knew the answer is pi over 8. So, for those who are curious to how this is actually solved, so from 0 to 1, this is x minus x squared dx. Okay, this, if you complete the square, you get 1/4 minus x minus a half squared. Okay, so completing the square will give you this. If you complete the square, and I know it looks nasty because you have fractions, but it is something that you do have to get used to a lot, especially in competitive integration bees. So completing the square, right? And then look at this. Let u equal x minus a half. What do you get? What is this? This is an area of a partial circle. In this case, we have an area of a semicircle. So we get pi over 2, and then times the radius square, which is 1/4. Right? 1/4 is r squared, because the radius is 1/2. So in that case, our answer is pi over 8. Okay? It's just an area of a partial circle, an area of a semicircle with radius 1/2. Here, I skipped because I was a little too intimidated. I did skip this, and then I just went on to like here, and I'm like, you know what? Let's bash it. So I bashed this integral, right? The only thing I written down, just for the sake of time, was like sine of x sinh, right? Well, I actually abbreviated sine of x, right? Here, like this. And I have to be careful, sinh, cosh. You don't want to get mixed up with your abbreviations, right? And I knew this is the same thing as the I had, so I knew I'm going to get 2i, and I have to like divide half to the other side. So this is where I'm like, okay, I know the answer now. Sine of x, cosh x minus cosine of x, sinh of x. And then because it recursed, it was recursive, I do a half because it was the same integral, except, so it's pretty much this, I equals whatever we had, and then minus I. So I did 2i, and then my answer that I had divided by 2, in which that's what this is. Okay, so that's how I quickly integrated that. Here, I was kind of like, at first I was going to use the trig identity, but then I'm like, wait, 0 to pi over 3 minus x. Huh, let's use King's rule, right? So, and that's what I did. 0 to pi over 3, right? If I had sine of x, and I had cosine pi over 3 minus x, right? By King's rule, let u equal pi over 3 minus x. This is going to give me 0 pi over 3 of sine of pi over 3 x cosine of x, right? Then add these two integrals together, right? If I add these two integrals together, so this is technically a half of sine of cosine of this plus, you know, cosine of and sine this. It's a sine cosine cosine sine. That's a sine law. So pretty much this is x plus pi over 3 minus x. The x's cancels out. And sine pi over 3 is equal to root 3 over 2, right? This, not the integral, okay? So, what we have is root 3 over 4 times pi over 3, and that's where I got my answer, this answer. Okay, so that's the fastest, that's mentally the fastest way to solve this integral, okay? So this was kind of what was happening in my head. I just have to display it for those who are semi-new to my channel. I have a training called Queen's Rule. It's in the Integration Bee Training Advanced playlist, and you can take a look at that. There's like so many tricky manipulations that you can do with this, and this is one of them. So, but yeah, but mentally this is what I did, and so I was left, you know, I was like, okay, it's just Queen's Rule, and I ended up with this, right? Square root of 3 or sine pi over 3, and I went on with my day. Okay, so that's the fastest way you could do with that one. Here I skipped and I went to here, and then here I noticed, like, wait, this is just a geometric series. What the heck? Like, I thought the sum did spooked me a little bit, but I realized, wait, x to the power of k, that's a geometric series. This isn't Taylor series. So this, you do have to be careful. Please be careful. This, I feel like this killed a lot of competitors because it's a common mistake. Don't forget k equals to 1. Okay, it's not k equal to 0, it's k equal to 1. So what this means is we have from 0 to 1, right? So we know that this is, okay, negative 1k, and we have x squared to the power of k, right? So we know that our denominator is 1 plus x squared by geometric series, right? But it's not just this, right? K equals to 1. So what that means that our first term is negative 1 and then x squared. So what we actually have is negative x squared on top. Okay? This is our integral. It's not it's not just arctan, it's not pi over 4, right? We have a negative x squared on top. Okay? And so now this is equal, we could do minus 1 plus 1, right? So we have this, minus 1 dx, and this is simply pi over 4 minus 1, which is the correct answer. So that's that, and then I went back and I'm like, alright, let's go back to here. Alright, 19, and the square is a distraction, so I just want to focus on this. I'm like, okay, what on earth is this genuinely, right? So I paid attention to this first, and then add cosine x later. So I was like, okay, what is this, right? That 2 pi over 3 is so distracting, I'm just going to ignore that and let it be like a, right? So cosine of x plus a is equal to cosine minus sine. And then this is where I realized, like, oh, wait a minute, this is actually not that bad. This is actually not that bad, because when you add it together, right, you get 2 of cosine of this. So what I actually have is 2 cosine of x times, and then and then cosine of 2 pi over 3, which is, for those who don't know, 2 pi over 3 is like here, and you notice that this is negative 1/2. So I have negative cosine. And this is where I started freaking out, because remember that I have cosine of x. So what this means is that because if this portion is negative cosine of x, if this is equal to negative cosine of x and this is cosine of x, that means that this whole thing is equal to 0. And I'm like, wait, but this is indefinite integral. And so I'm like second guessing, like, wait, did I do something illegal? Did I do something wrong? And I don't think I did. I checked my answer. I'm like, I didn't do anything wrong here. And I'm like, screw it, I'm just gonna answer 0, because I mean 2 pi over 3 is negative 1/2, right? So that's where I'm like, this is a negative cosine of x, so I guess it's 0 squared is equal to 0. So that's where I'm like, you know what, screw it. I mean, I did nothing wrong, so I answered 19 as 0. I noticed I had a lot of time, so I'm like, alright, let's do this. And I realized this is a lot easier than I thought, right? Sine are actually, I think it's best if I write it, because there is a lot of trig identities going on in this integral. Sine 4x is equal to 2 sine 2x cosine 2x, right? And I have what? Cosine of x on top, and I had cosine 2x, and I had sine of x at the bottom, right? This cancels out, and this is eventually going to cancel out with this, because this is 2 cosine of x, but this part here canceled with that, right? So my answer, so what I have is pretty much the integral of 4 cosine square dx, in which I was able to integrate very quickly, right? This is just one of these, right? So this is 2 plus 2 cosine of 2x, and so our answer is 2x plus sine of 2x. Okay? A lot easier than I thought. Just a lot of canceling trig identities. I skipped this because I didn't want to deal with that. I know myself very clearly that I'm not going to be fast enough, so I did this first. Now here, I'll show you the trap first, and then I'll show you the fastest shortcut. So the trap here, here's what I did. Okay, I fell into a trap here. This is one of the greatest examples of how to trap an advanced player and favor the beginners. Okay? So, for an advanced person like me, I let u equal x minus a half. The reason why I want to do this is consecutively, I mean, technically these linear polynomials, they're consecutive by a half. So, what this means is I have negative half, I have like 10 minus a half. I wrote it like this because I didn't want to actually, you know, simplify the whole thing. And so what this means is I have u, and these two is like, this is technically u plus 1, this is u minus, I'm sorry, u plus a half, u minus a half. So I have u squared minus 1/4. Yeah, that's why, I think that's why I got the wrong answers, because it wasn't 1/4. I accidentally wrote it as 1/2. U squared minus 1/2. But essentially, this is supposed to be u squared minus 1/4. And then you do a u substitution, another u sub, right? Now you see where this is going? You see how nasty this is, right? Now you literally have 10 minus a half squared minus 1/4. And then here you have like 0. Because this is a squaring, this is 1/4, right? So now you have w, and then you have this, right? The 0 we don't have to worry about, but this part is nasty. So we have 10 minus a half squared minus 1/4 squared, which I believe this should come out as 2025. But I didn't do that, you see? Right, so that's the trap that I fell into. You want to avoid this at all costs. And now, let me show you the shortcut that you're supposed to do. You want this, distribute this to here. Okay? So you should get 0 to 10, x minus a half, x squared minus x dx. Now, I know I'm gonna sound crazy, but just trust me on this. Just trust me on this. Let u equal x squared minus x. Right? And you're probably thinking, Silver, you're a goddamn psychopath. First of all, I didn't come up with this. The comment section did. Someone, or actually that would be rude. I'm sorry. That would be rude of me to mention. I apologize. But I didn't come up with this. It was given. I was told in the comment section. Du is 2x minus 1. Oh, would you look at that? What is this? This is 2x minus 1. Oh, would you look at this? This is technically the same thing, but it's just divided by half. right? So this is equal to half of, and then 0, 100 minus 10 is 90, right? And then we have u du. Okay? And this is equal to u squared over 4, 0 to 90. We have, what, 8100 over divided by 4? Huh. Oh, it is 81 times 25. Yeah, okay. Yeah. And that's how you get the answer 2025. Okay? Very crazy, right? I would have never thought of this, right? This is how you favor beginner competitors and trick the advanced integrators. So, yeah, that can happen. Rarely, but it does happen, right? So, yes, be extremely careful. There are some times where taking the beginner way route is the better option, and the biggest reason behind it is because of the bounds. Okay, and my last one I solved was 11. I'll make sure I'm not missing anything. Yeah, 11. Oh boy, 11. I didn't know how to. I was actually my anxiety kicked in when I had to solve 11. So from 0 to 20, and obviously I don't want to, there's too much going on, so I don't want to turn it into a sum. So I want to deconstruct this, right? I want to deconstruct this integral here. So I'm like, okay, from 0 to 1, right? From 0 to 1, I get, what do I get? Right, 0, 0, okay. So that's just 0. From 1 to 2, right? I plug in 1, 1/2, but remember this is a ceiling function, so this is 1, okay? And then I'm like, what's next? Okay, so from 2 to 3, I get, what? From 2 to 3, I get 2 here, just 1, right? 3 to 4, I get 3 here, but then it's 2. Because the ceiling function of 3/2 is 2, right? And then you keep going, right? 4, 2, etc. And then you keep going all the way up to 19 to 20. Oh, it's 19 over 2. 19 over 2, that's like what? 10, right? So, and that's where I'm like, oh, wait a minute. This is literally this. 19. I'm sorry, 19. This is literally this. Does that make sense? So this sum is literally this. And then I didn't see it that way. I was like, I don't know if it was, I don't know. My brain was contorted. So I deconstructed it and then turned this, even though this is literally this in summation. So here I was like, okay. So, and I noticed a pattern, like this is literally 2 plus 4 plus 6 plus 8 plus 10 plus 12 plus 14 plus 16 plus 18 and then plus 10. Right, the 10. Because I had 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 9. Because this covers 18 terms. And then my 19th term was 10. Right, my 19th term. Okay. So I'm just fast forwarding, right? 1 plus 1, 2 plus 2, 3 plus 3. I just, edited it all up, right? And then I just add this whole thing up. Now, how do I speed solve this? Just like AMC, right? 10, that's 10, 10. This is like 30. Be very careful, okay? Keep track, 10, 10. This is not 10, this is 30. And this is 30. And then 10. And then what do you realize? Oh, I have like 60. I am missing it. Oh, 10's right here. Oh, be very careful. like I said, don't draw it out like this. Be more organized, be more organized than me. So we have 10 here, 10 here, 10 here, 10 here. So 40 plus 60, this is equal to 100. And that's the correct answer. Okay? So that sum is equal to 100. Alright. And that's the entire qualifying exam. Okay? So, yeah. And it did, I'm gonna be honest, this is a lot. The qualifying exam has been a lot easier. It does feel a lot easier than the previous years. But I genuinely think that this is a perfect qualifying exam. Like, this year's qualifying exam was perfect. I feel like this was a perfect qualifying exam. Okay, so yeah, that's how I solved this qualifying exam, and I got 19 out of 20. Okay, so I hope that was kind of helpful. I know I blast through all of this very quickly, but it was just, I just don't want to be redundant or slow. So, but yeah, again, if you're new, I have an entire whole playlist of integration bee training. So if you want to get into things like this, my playlist is there for you to check out. Okay? Alright. I hope that helps. Thank you guys so much for watching, and I'll see you guys in the next video.